Now, every directory that we are storing in this directory hierarchy that we took a look and in this tree over here needs to store different kind of information. This information, we could call it as metadata. And a directory metadata could contain name of file. So file that's stored inside that directory, when it is created, when it was last modified, who is the owner, because there could be multiple users on a system. Imagine a system in one of the computer labs or in libraries. So different people could access that. If it's a computer lab system, different students affiliated with that organization to which this computer lab belongs to can log in with their login IDs or their user IDs and access their own profile. So there could be different owners for the same system. Then for all the data, we could have different permissions. So such as, is this file read or write? And things like from where to where does this file begin? On the large consecutive blocks that are stored on any storage device. So we can imagine in a storage device as an array of blocks, block 0, block 1, block 2, block 3, and so on, until the capacity of the storage device supports, and depends on the block size. It could be 512 kilobyte each block size. And then we need to know, so for our operating system level abstraction, we need to know that wherever this file is stored, which block does this file starts? And then what is the length of this file? So every file can have such information related to it. We can call it as metadata. Now this file could be stored inside a directory. The directory only needs to manage the data in sense of what files is it storing, what are the inode of these files, or what directories it is storing, and what are the inodes of these directories. That's it. So let's start talking about creating. Creating files. In a Unix-based system, creating files happens with a simple system call such as open. So for example, can have int fd equals to open system call file foo.txt, comma, we can have 3 different arguments in this call. The first argument is the file name itself, as you see over here. The second argument is different flags that gives us more information about this particular file or how to create this particular file. So these flags could look like a flag called ocreate that stores the information about, or that says the command about create if it does not exist. So if this file named foo.txt doesn't exist in this directory, then create that. And another flag could be WRONLY. This flag says that I want this file to be write-only file. And another flag could be such as OTrunk. This flag says, let's say, if there is another file inside this directory with the same name, so if it already exists, then truncate it to 0 byte. So basically, if there is another file with the same name inside the directory, delete all the content inside that file, because now we want to write new content to this write-only file that we are opening or creating. So we can have such different flags to give more information about what is the type of the file that we want to create, what are the things that we want to do with that. What if there is another file with the same name, what do we do then? Things like that. And the third argument we can have about is permissions. So this flags could look like the flag that says, so this flag says permission to read. Or we can have a flag called IW user. This flag would say, as you could guess, permission to write. So the third argument is permissions. Second argument is giving an information about, some more information about what to do if there are other existing things in this directory with the same name. The first argument is the name of the file itself. And what do this open function returns? As you see here, it's returning int fd. This is a file descriptor. And file descriptor is an integer, as it's represented by the type int. File descriptor is private per process. An operating system can have multiple processes, and each process could access different files. So each of these files has its own, when we open each of these files, it returns an integer, which is file descriptor, and that's unique per file in a process. And this could be visualized, or this could be understood as some kind of struct in process struct. This file descriptor is used in Unix systems to access files or to access created open files. We could represent it as, so let's say if we have process struct, then inside that process struct, we could have another struct called file, which is pointer of arrays, some other thing, obviously in the struct, proc, so on. So what does this say is it's a simple array with max a number of open files. It tracks which files are opened on a per process basis. And it is important to track this information because we can access the content inside the file, or we can access the file only after opening the file. So definitely somewhere we need to maintain what are these open files, and each process can have one or more open files. So that leads to this organized struct of information that stores these content. Now that we know that now each process can have multiple files that are open, and how do we open or create these files? What if you want to see the process? Like basically, if you have access to command line, you can quickly open it right now. And what if you want to open a file, or let's say open a directory, or opening a directory means making a directory, right? Creating a directory, we call it as making a directory. Then we could use a tool called strace, which we would be using repeatedly in this lecture. So I would highly recommend you to SSH or open your command line. If you're using a Mac system, open the terminal. If you're using Windows, then open SSH to a system which has an access to terminal, or your visual programming API, open that, in which you can type commands. Or if you're using a Linux system, please open the terminal. The best is using a Linux system, open the terminal. That's the easiest. So now if you have your terminal open, then you could use a tool or a command line called strace. And what this tool does is it helps us to track what system calls program makes. So let's say if we want to now, we saw what do we do while opening a file. Now, let's say if we want to open a directory, that means making a directory. It's simply done by the command make directory, mkdir, in Unix system. And many of you might be familiar with this command already. So to your command prompt, which you have it open in the terminal right now, you can try something like giving a command like strace mkdir, maybe your name, a directory with your name, or a foo. What it would return is something like mkdir. So it's making a make directory system call for the file foo with some permissions. It could be 0777 that is accessible to everyone permission. Sometimes you would have changed the permissions for a particular file using the command chmod 777. That's the same 777 that we represent here, equals to 0. That means you're able to successfully create this directory inside, create the directory named foo wherever you are creating it inside that directory or inside root. Now, every time we create a new directory, what it returns is an empty directory, right? Because we just created it. There is nothing inside it. And an empty directory stores two entries. One is dot, which represents itself. And second is dot dot, which represents its parent directory. So a directory is definitely inside some parent. All the directories on your system is definitely inside some parent directory. This parent directory could be at the lowermost level, it could be the root, right? Or some other directories. And the directory appointed to the directory itself is also important. So these both are the information that as soon as we make any directory, it would have these two entries within it. So if you want to play a bit more with this strace command, we could do something like, you could issue some command like strace cat foo. What cat does is dumps the content of the file to the screen. So when you are dumping the content of the file foo to the screen, what are you doing? We are reading the file and we are already into the accessing them. We created the file foo. Now we can do different operations on this file foo to access the file foo, such as read it and write it, either the entire file sequentially or read it from a particular location or particular offset inside the file, or just update the entire file itself, or update just a particular content or a particular content at a particular offset inside the file. So all these access operations we could do. But here to show how the strace works with this simplistic command strace cat foo, before we need to ensure that the foo is created. So we open file foo already, as we talked about earlier. And at that time, foo would be empty. So what this would return is nothing but the string of system calls to read an empty file. But let's say if we have something in our foo, for example, before even we gave this ftrace cat foo operation, we did command line. We wrote some other command lines to write some content inside the file foo, such as echo hello. That would echo the word hello onto the screen. And then we want to store this word hello. So we direct the word hello into the file foo. And then, so first we do this, and then we do strace cat foo. So now foo has this string called hello inside it. Now, when we do strace cat foo, what it would do is, first, definitely we have to open, in order to access any file, we have to open that file. So we would open foo. It would open with some flags, such as it could be read only. or large file, and it returns the file descriptor, which is an int. That's 3. Now, why did I put file descriptor as 3? Is 3 my favorite number? Or is there any more technical reason behind that? Well, the file descriptors for any directory, file descriptors 0, 1, and 2 are already pre-taken, not available to take. That is because file descriptor 0 is standard input. File descriptor 1 is standard output. So this is for read, this is for standard write, and file descriptor 2 is standard error. So high likely, your system, when you run *cat foo, high likely it would return 3. That's my guess. It could be anything more than this as well, depending on how many files you have open in your system at this time. Then what it would do is pass a read system call with this file descriptor 3, the string to be read, and the byte size. So here we are storing it into a 4 kilobyte size variable. And this read would return the number of characters it read from the file. So here 5 digits are for the word hello itself, plus the end of the line character. So in total 6, that's what we return. Then the string would be write to the standard output. So as we just said over here, 1 file descriptor means the standard output. So we would write this to the standard output, write the string hello. It's a 6-character string. When it's done successfully, we return, yes, we wrote 6 characters. That would write the word hello on the screen. Finally, because it's a iterative file call until we are done, until we reach the end of the file. So we would again try reading file 3, that's the file descriptor. But now it would return with null because everything that this file stored was this word hello, and we already read that. So it doesn't store anything more than that. Still, we use some space, 4 KB, the same space, because we didn't read anything at this time. So we read number of characters, we read as 0. Once the read command returns with 0, then we know that we are ready to close the file with file descriptor 3. So all this system calls happen just behind this sweet little command cat foo. So this *trace tool is very helpful in understanding what are the underneath system calls that are happening. So feel free to play with that. This is just one simple example. So now, as we have already started twiggling with accessing files, and we already saw an example of reading a file foo, writing a file foo with echo command with word hello inside it. Now you can also try a command on your terminal, something like *trace dd if equals to foo. of equals to bar. This command will help you to understand what happens with write call. So do it on your own, do it on your system. It's not very complicated, so I'll leave up to you to understand and just observe what are the underlying system calls that happens with this command. Now, let's say, so we saw how we can read the entire file, how we can write the entire file. But let's say we don't want to read the entire file. We just want to read entire file sequentially from all the way from beginning until the end, which could be done by this set of system calls. But we don't want to do that, but rather we just want to read randomly at a particular offset inside the file. Then what do we do?